Hello everyone, and welcome to our presentation on the discrete element method. This project was put together by myself, Runhang Wang, He Choi, and Fanghao Yu. As an aside, I hope you're all staying safe during these strange times, and that your studies haven't been impacted too much by the shift to online learning. We'll all get through it together. But for now, thanks for listening. On to the discrete element method. What is the discrete element method? Well, it's essentially the simulation of the motion and effect of a large number of small particles. Since each particle, or grain, or capsule can be thought of as its own individual element, the model is comprised of discrete elements. Here's a short video of particles moving through an auger as simulated by DeEM to give you a sense for what exactly this method is all about. Particles, perhaps agricultural grains like wheat or oats, spawn with random orientations and velocities in some gravitational field at the top left. As the auger begins to turn, it shifts the locations of the particles, which move in the direction of the axis of rotation. Radial boundary collision conditions on each particle give the particles a feel for being solid, and the elasticity of each collision is given a value that mimics reality. On the bottom of the video, you can see that each particle has its own size, which here also, likely, translates to its own mass. This is also very important in determining how momentum is conserved. Note, while seemingly very natural, that the simulation isn't perfect. Some particles are recoiling after they've come to rest with non-physical final velocity vectors given some collision with another grain. When modeling, we hope to come as close as possible to reality, but rarely do we get all the way there. Physical models like these effectively come in two flavors, which separates them based on how they've discretized individual points in space. Those flavors are Lagrangian and Eulerian. In EME 521, we've been learning and practicing Eulerian methods for most of the year with the FEM script we've been compiling, so you are likely familiar with this method. The images on the right-hand side of the screen should give you some feel for how these two modeling styles differ, but let's go through them explicitly. In Eulerian models, the space is continuous and fills the void and volume we're considering. In Lagrangian models, space is discontinuous and is populated by particles of varying masses and sizes. In between the particles, there is either void, or air, or water, or some other media as defined by the model. In Eulerian models, differential equations and integral calculus relate stresses and strains via constitutive equations. Nodes and elements can and should be defined in matrix notation to simplify this process. In Lagrangian models, Newton's classical mechanics dominates, as each particle is given positions, velocities, accelerations, forces, rotations, and anything else that may be relevant to the model. While you could say that calculus is technically necessary for these models, programmatically time-stepping through the kinematic equations via a Verlet algorithm, for example, is conceptually much easier to visualize and mathematically much simpler. In Eulerian models, the resolution of the model is also filled throughout the grid. In essence, there is no empty space. In Lagrangian models, the resolution is as small as the smallest particle, meaning anything not simulated by a particle is ill-defined. In essence, there are regions of unmodeled space. Finally, in Eulerian models, the computation required to model the space is much cheaper on the calculating body, since all the physics is applied at the nodes. In Lagrangian models, the same amount of computation is necessary everywhere there is a particle, yielding potentially expensive results. Current computation makes most of these models feasible to the layperson, but massive accountings with hundreds of thousands, or even more, particles can't be processed immediately. And since time is money, Lagrangian and Eulerian models each have their own domain of use. As I alluded to in the last slide, why would you want to use DEM when it's potentially more computationally expensive at the larger scales? What about DEM is unique enough to choose? Well, each particle has its own rotational, positional, radial, and momentum vectors that can be calculated using simple Newtonian physics. Conceptually, how the particles interact, even with the inclusion of frictional forces, is very easy to understand. And since Newtonian physics is predominantly all that's required, animating a model that displays your simulation is a relatively natural way to communicate the results. Second, the simulation only consists of 3 parts. First, the initialization step, where the particles are given some mass, position, velocity, etc. Second, the time incrementation step, where the positions, velocities, rotations, etc. of every initialized particle are updated based on the forces each one has experienced on that time step. And finally, the post-processing step, where particles are drawn to a display or outputted to a data file. For smaller numbers of particles, the time stepping and post-processing can happen nearly simultaneously, or technically as fast as the frame rate dictates. But for larger numbers, substantial time must be spent on the post-processing step. Lastly, and accordingly, there are some cases when the DEM is the ideal model, namely for separate discrete particle situations like colloids, milk for example, granular matter, powders, blocky or jointed rock masses, bulk materials in storage like our grain in the auger from earlier, and progressive fracturing and failure of a material. Thus, there are industrial applications for DEM. Those include chemicals and chemical engineering, like when modeling molecular movements and interactions, pharmaceuticals, like when blending or milling, ceramics, like when modeling fractures given some applied force to the ceramic, metals, like when modeling bending or failure or simulating an applied powdered layer, and food and agriculture, referring again to the original video we watched regarding grain transport. Here are some images that illustrate the industrial applications. Transport and mixing is the obvious goal from the image on the left, and fracturing and precise deformations is the obvious goal of the model on the right. Note that circles and spheres are used for simplicity's sake when describing particles, but this does not necessarily have to be the smallest modeled unit. So, as we've seen from the past couple slides, we can summarize when we would use DEM into a schema of advantages and disadvantages. Determining what you want out of the modeled result can provide insight as to whether or not you should attempt to use DEM for your own devices. For starters, DEM gives you a micromechanical level of analysis, aptly discretizing every single position, velocity, and rotation for every single particle across the entire duration of the simulation. Conversely, that level of detail is computationally intensive. If individual particle interactions is of paramount importance, choose DEM. Secondly, DEM gives you accurate materials modeling when experiments are difficult to conduct or are cost prohibitive to conduct, at the expense of being able to validate those models. DEM works best as a near estimate of how particles will interact, but can't be solely substituted for an honest real-life experiment. Third, while you can identify the regimes when DEM would be most powerful and apply it to FEM and/or CFD methods, the fact remains that the smallest unit particle you have is indivisible and perfectly rigid, meaning you can't model what would happen if that unit were to fracture and break, unless you model that fracture with another DEM technique. But you can see how, at even one level of recursion, this massively increases the cost of computation. Again, determining what you want out of the modeled result before running any model is imperative before choosing any model. Now that we know a little bit more about DEM, what it is, why it's unique, and when to use it, we can talk about how it was developed. Our story starts in 1697, when Newton formulates his ideas about classical mechanics. I'm not going to dive into this development more than how he codified the physical laws the DEM is based on. There are about 1,000 different biographies on Newton and his systemization of physics, and if you're curious, I strongly recommend you pick up one. Personally, I've read through one about his co-development of calculus, and it's honestly fascinating. Next, we skip about 300 years into the future, where then PhD candidate Peter A. Kundal is writing his 1971 thesis, The Measurement and Analysis of Accelerations in Rock Slopes. In his PhD, Kundal describes elements of rock as rigid 2D masses based on finite difference principles. While nascent, DEM is not fully formed yet. The looping GIF is actually an image of Kundal as modeled by DEM. Over the next few years, Kundal formally codes his thesis analysis schema into a restricted Boltzmann machine code, which is an RBM code, allowing machine language to describe the rocky interactions without the need to hand calculate each collision with each surface. The official formulation of DEM into Fortran happens 5 years later in Kundal and Strack's paper, A Discrete Numerical Model for Granular Assemblies. It finally sets the groundwork for DEM as we know it today and becomes the most widely cited paper in geotechnique, currently with over 14,500 citations. 6 years after that, in 1985, two major events happen in the world of DEM. The first, Kundal and Hart resolve issues with DEM and can now formally apply it to 3D models, and Williams, Hocking, and Musto expand the discrete element method into a more generalized discrete element method. This generalization method begins to bridge the gap between Lagrangian and Eulerian methods. In 1992, She uses DEM to formulate discontinuous deformation analysis, a finite element method that includes the interactions of independent particles at discontinuities in fractured and jointed rock masses. And finally, we push on into the present day, where many hybrid finite discrete element methods exist, specializing the model and tailoring the methodology to one form or the other depending on the type of regime desired.
Okay, so now let's begin the next section. This is Renheng. We are going to discuss about the general principles. And so from here, we can see there are two fundamental theories that will support the DEM methods. So first, it is the Newton's second law of motion, and the second is the force displacement law. So for Newton's second law of motion, it means in an inertial frame of reference, the vector sum of the force F on an object is equal to the mass m of that object multiplied by the acceleration a of the object, and the well-known equation F equals to m multiplied by a. And also for the force displacement law, it means, here it depends on the models that are designed for the smooth particles of the regular rounded shape, and they provided by the force displacement laws that account for both normal and tangential interactions. And also for here, you can see they have their own interrelationships. So assume here we have the stiffness and frictions as the force displacement laws, and by effecting with the force boundary conditions, they will directly affect on the Newton's second laws of motion. That means make the moving of the object become possible. And by the effects from the Newton's second law of motion, and it will affect on the force displacement laws by the displacement or velocity boundary conditions. And for here, so we can go in details to discuss the Newton mechanics and the force between the particles. And to be more accurate, the mechanics contains two elements. The first is the conservation of momentum. So as we know, all the knowledge is from the momentum, and also about the particle motions. And both include the translational and the rotational. And also for force between particles that I mentioned before, in the last slide, we can regard several different kind of force, especially like frictions and stiffness. And also here are the methods that also mentioned by previous sections. So the soft sphere or the hard sphere, and also their characteristics was already discussed. So I'm going to change another perspective towards these two methods and to discuss why one of them is much more welcomed. So let's make long story short. Compared with the hot sphere method, the soft sphere method is more common and accurate. So what reasons? So there are currently three reasons. So firstly, the smaller overlaps between those two particles are allowed, although those particles are rigid. So just for its properties, it is softer compared with the hot sphere method. And for the second reason, the evaluation toward forces are more accurate. And for the third reason, the simultaneous contacts become possible. And you can see like the image on the right side. It's just like a momentum collision. And you can see on the middle part, so they're overlapping. So that's the most special characteristic for the soft sphere method. Okay, so derived from that image, now we can construct another model which is presented on the right side of this slide, which name is contact force models. So for these models, they interrelate amount of overlaps, both normal and tangential overlaps. So in terms of these two objects, in order to determine the magnitude of forces, so they are established. You can see from the image here, the force is interrelated with the time going, and also it depends on the whole process of collisions. So two balls collide and bouncing and separate. And you can see during the process of collision, the total forces accumulate, and with the bouncing and after the separating, the force decrease until zero. And also not only the collision forces are regarded, also we can consider other non-contact forces in DEM methods. So for instance, like electrostatics and like the van der Waals forces, they can also be simulated. So from these examples, we can see also we establish other types of models and with different processes, but by the appropriate using of the DEM methods, the result and procedure still be very helpful, and we can approach those answers more accurately like we want. And so let's pass the topic to the next section.
Generally, there are two different main methods in DEM, discrete elements method. The first one is a hard sphere approach. In this approach, the action forces are assumed to be impulsive, and therefore the particles only exchange their momentum through collisions. And forces between them are not explicitly considered. Only one collision occurs at a time, and there are no overlaps between two particles. The other method is a soft sphere approach. In this approach, the particles are also assumed to be rigid, but the small overlaps are allowed to represent interacting forces during contact like this. Because of the existence of normal and tangential contact forces and non-contact forces, soft sphere DEM represents more realistic bulk material behavior. Also, because of the nature of this approach, simultaneous contacts are possible. The soft sphere models are most accurate, therefore it's commonly used in DEM. I will talk about soft sphere method governing equations after this. In DEM, the particle motion is calculated based on the Newton's equations. Each particle in granular flow has 6 degrees of freedom, and as a result, it has two types of motion, rotational and translational. The rotational motion is calculated based on this first equation. It simply states that resultant contact torque acting on this particle equals to the moment of inertia of a particle times angular acceleration. And this angular acceleration can be rewritten as d omega over dt, the time derivative of omega. The translational motion is also calculated based on Newton's law. So we have equation F equals to ma, and F here is the sum of forces acting on the particle, which are gravitational force mg, the red arrow in the slide, and contact force, whatever that coming from the interactions with contacted green particle here, and non-contact force coming from the interactions with non-contacted yellow particle. So what are those? Contact force is the sum of normal contact force, the green arrow in this figure, and tangential contact force, the yellow arrow in this figure. Let's take a look at the leftmost figure first. Particle I and J start to contact at point C, and then these two particles are deformed in subsequent movements. Delta N represents the normal displacement, and delta T represents the tangential displacement. Figure B shows the constitutive model of the interaction between two particles. A spring here is used to simulate deformation damp, and a damper is used to simulate the damping effect. So the normal contact force is defined as minus normal stiffness of the springs times normal displacements minus normal damping coefficients times normal relative velocities. And tangential force is calculated in same way basically, but all the parameters of tangential. For non-contact forces, we only considered gravitational force between two non-contacted particles. This pulling force is defined as gravitational constant g times mass of blue particles m1 times mass of green particle m2 divided by distance r. For more accurate models, you can consider further non-contact forces. For example, molecular forces such as electrostatic. Electrostatic is calculated by Coulomb's law. Coulomb's constant K times magnitudes of electric charges Q1 times Q2 divided by distance r. That's how it calculated. It's pretty similar to the gravitational force, but something about electric charges. After the accelerations calculated, they are numerically integrated over a time step to update particle velocities and positions. So Vt and Xt here are updated to Vt plus delta t and Xt plus delta t, and so on. Delta t is one time step. And in DEM, the velocity is constant during one time step. And I only showed the example of translational motion here, but the calculations are very similar for rotational velocities and particle orientation. This flowchart summarizes the basic principles of particle behavior as they are simulated using DeEM methods. First of all, by using contact mechanics, DeEM is capable of calculating the forces acting on the particles. Once these forces acting on the particles are known, accelerations are computed using the Newton's law of motion. And then velocities are calculated using numerical integration. And after it updating particle positions, the algorithm searches again for the contacts. And this whole cycle iterates.
So here we have the hand calculation example. So the discrete element method is a finite difference scheme, and Taylor series approximations are commonly used to derive finite difference approximation for derivatives of different types. Basically, Taylor series is a representation of a function as a infinite sum of terms that are calculated from the values of the function's derivatives at a single point. So there's three methods of forward of the Taylor series: the forward difference, backward difference, and the central difference. So from the picture below and on the bottom and the three equations on the right, you can see how each method is the principle of each method. So we decide to use a very simple and straightforward 1D example to demonstrate the DEM method. We use this pendulum motion, and our goal is to calculate the angular displacement, angular velocity, and the angular acceleration. We need to mention that there's no damping is considered. So here we have the fundamental equations. You can see the angular velocity, angular acceleration, linear displacement, and the linear velocity. It's very basic, just basic physics. And as we know from the picture, the driving force of the motion is basically the component force of the gravity. And also from the Newton's law, we have the force equals to the minus mass and multiplies acceleration. So it's easy to derive the equations down the bottom. So by forward difference, we can get the three equations. that we use to calculate. We use in the calculation. So here's our initial conditions. So we hold the ball at the beginning and release it instantly. So we assume the mass is 1 kilogram, gravity acceleration is 9.8, length of the rope is 5 meters, and the initial angle is 30 degree. And I use this. I test our results. So as you can see from the chart, it's the angle is decreased, and also the angular velocity and the angular acceleration also decreased. So it's straightforward from the plot on this page. So as you can see, it's a very typical pendulum motion. So yeah, and yeah, what I also need to mention is the difference between the numerical solution and the analytical solution. So as you can see from the picture on the bottom, there's a slight difference between the numerical solution and the analytical solution. Yeah, so why this happens? It is because for the discrete element method, we use, because it use Taylor series, so it neglects the first derivative and also the second derivatives. As you can see, for the central difference, it neglect the second degree derivatives. So the discrete element method has errors, but it's within an acceptable level. So here's our numerical examples part. We use a Python script we made and to demonstrate this simple example. So as you can see from the animation, we can algorithmically apply the general principles and the governing equations. So our assumption is that it's in a gravitational field. The particle is free to rotate and there's no friction. So now let us add the friction into the particle's motion. As you can see from its bounce, it's stopped at the end. So approximating friction from the coefficient of restitute for these elementary examples, and yeah, and here's a more complex example. Yeah, so we add another particle, and we also consider the collision effect, the particle's velocity and the rotation. So initialize with a random velocity vector. So the civil are meant to approximate golf balls to, demonstrate the physics. So the system is pretty elastic. And as Alex mentioned before, so each particle has its own rotational, positional, and radical, and the momentum vectors that can be calculated using the simple Newton physics. So here's another example. So extrapolating to the to n particles, more particles we can see. So each with a random initial velocity vector, as you can see from the animation. Yeah. So yeah, I think the animations before has demonstrated the principle and the characteristics of the discrete element method. So yeah, basically that's our numerical examples.
Okay, so continue with the topic, but I will move it a little bit to agricultural. So how does DEM apply on the agricultural perspectives? So you can see the hooper here. So it is for grace falling. In the past, people they have to filter it manually or even pick those dirt, rock, or shells by themselves in hands. So that was really inefficient. With this hooper, so like the dropping, accelerating, to make those grains falling in specific speed, and because with the different density, I mean the mass for their own properties, so those different materials like the shells, rocks, or sand will be moved to different distance compared with the grains. So that make the filter works become more effective, and people can remove those unnecessary goods easily. And now we can switch the topic back to industrial. So this shows the concrete mixing, and it is a little bit different with other examples because it is the use of cohesion. It's a really good example. It is originally a video here, but in order to make the story simple, I just picked the beginning and the ending pictures. So by the first step, the aggregate and sand are added, keep the steering, and then cement are added, and then water, but still keep steering for the whole procedures. So after add the water, the liquid bridge established to form the cohesion. So this is really essential part. For the next step, the cement paste and mortar emerge, depends on cohesion. And then the liquefaction happened. So this is the hand behavior. So after these procedures, the concrete are almost done. And as a PNG student, I think it is necessary to regard the interrelations between the propant deformation and the application of DEM methods. So you can see on the right side, the image presents several types of propants. So for the conventional frac sand and unconventional ceramics. So how could they build a relationship? So firstly, propants are very important, very essential for hydraulic fracturing. And how it works, propants, they keep the fracture opened, and I will show the related picture on the next slide. But before that, I still have to provide another simulation-related concept, LIGGGHTS. So this simulation originated from another complex name simulator. That name is LAMMPS, Classical Molecular Dynamics Simulator. So based on this type of simulator, so LIGGGHTS indicates the LAMMPS improved for general granular and granular heat transfer simulation. So this is really important for the propant deformation and the DEM method application. So now look at the image on the right side of this slide. You can see how propants work. They keep the fracture opened after injected into the formation, and they support each other to guarantee they will not crush and make the closure for the fracture. And actually, before discussing how DEM applies, I still have to provide some conditions or at least assumptions. So how propant deformation fit for the DEM methods. So firstly, the shape of those propants must be spherical, and secondly, each grain must be individual. And also the third assumption, so those grains can affect each other at the only touching points. Okay, try to make this part as brief as possible for the series. we have to borrow some ideas from the source sphere method and to calculate the overlap between the two particles. You can see the formula and the image on the left. And then we can take the overlap to the image on the right to figure out the interrelationship when linear spring dash point model assumed for DEM. And after the multiple calculations, we can discover the theoretically, the magnitude of tangential force is bounded by the friction force. And then I will take to the simulation part. So for simulation, you can see the image on the right. So you can put these particles in 3 multiple by 3 millimeter Picard shape space and keep compressing with applied specific forces. And also for this experiment, we select specific types and also with their different Poisson's ratio and Young's modules. Propellant are classified as the frac sand, the resin-coated sand, and ceramic. And also there are 3 diameters are set. So we have the 0.005 millimeter and 0.01 millimeter and also the 0.015 millimeter. And also to make the conditions become much more ideal, the grains are supposed to be elastic, and also there are no temperature effect happens in assumption. So I divided all results into 2 groups, and this slide is for the first group. The purpose is still discussing about interrelationship between the deformation and force, but for this part, I'm going to assume the diameter of the propellants are the same, and we'll try to view how different properties that the different materials have. And you can see the trend of them are same. Although the values and the details are a little bit different, and you can see during the deformation, the ceramic is the most obvious when they are compressed. Okay, and this is the second group, different with the previous slide. Instead of discussing about how propellant material difference affects the interrelations, but here it discusses about the diameter difference. You can see the trends are really similar compared with the previous slide, but the details and changes of values are a little bit different. And you can see no matter what kind of propellant, the diameter with 0.005 has the most obvious changes in deformation and force interrelationship, and then the 0.01 and then 0.015. And for next topic, we can discuss about the granular avalanche. You can regard this concept like snow slides or landslides. So you can see depends on the picture from left. So different granulars are moved and then they are classified in different layers. So because their properties like densities and size and mass are different, so with the effect from the DEM, so they will have the different ability to move further or closer. And then they are arranged in different layers, in different distance, and determine their different properties. For instance, I can provide another example. So I was a geology student during the undergraduate time, and during the sedimentology classes, professor provided us lots of examples from the oceanic situation. So when the granular avalanche happened in the continental shelf or the continental rise. Also, she told us no matter from the sediment course or for the rock course, after we get the sample, we can classify the properties of different layers. And then we can even recover what kind of story, what kind of situation happened during the avalanche happened by understanding the different layers of those grains. And then for the next section, I have to mention the fault gauge. It is another geological concept, and we should consider this problem from the perspective of DEM methods. So we can see the picture on the left. And from the section A, the slip is simulated by providing a constant velocity to the block, which is shown in the blue color. And then the left side and the right side of the system are given servo-controlled stress boundary. The top and the bottom boundaries of the gauge are given zero displacement condition. And then for the section B, the grain displacement, you can see the Z component at the time when equals to the 4 millisecond and is simulated by the simplified model with the one-way coupling. And then we can move to the section C, the grain displacement at this time, still the same time, t equals to the 4 millisecond. It is simulated by the fully coupled model. And then we can see on the section D, the pore pressure change due to the slip simulated by the fully coupled model. And you can see those two cross sections are presented, which y and z, they both equal to 0. Okay, and here I can provide another agricultural example of DEM application. This is a potato segregation, a little bit similar with the Hooper I talked before, but for here, so you can see the potato, some of them contains rock or other materials inside, and they are carried on the conveyor belt. And you can see the pie chart on the right side. There are still a little bit the rock mixed inside. And how to make it more efficient? So actually by application of DEM. So in several procedures like in falling or in the other places on turning points or joints of the conveyor belts, the change of the speed and direction will segregate the potato and the rocks immediately because of their different properties. So which means the rock will be easily excluded from the potato. And actually there are still lots of other DEM applications I really want to talk about, but because of the time limitation, so I have to end this section. And I feel glad if it is still possible to share other application examples in the future sessions. And okay, here's the end of this part. Thank you.